Okay, we're going to start with any questions that you have from the review.
I'm handing it in.
Do you have any questions? Yes? Okay. I'm waiting. It's all good. Let's make sure this thing is recording properly. Make sure we're getting sound. Yes, we are. Okay, good. There we go.
Question 26.
26. When equal volumes of calcium sulfide and strontium hydroxide are mixed, so we need to know what happens with calcium and hydroxide and strontium and sulfide. So let's go to here. What? No. Because you're mixing 0.2 molar and 0.2 molar. So what are you going to get? 0.1 molar. Yes. And so you're just looking at, are they soluble or not? Not KSP, not anything like that. Just are they soluble or are they not? So you're going to look up on your solubility table. You're going to be like, with sulfide.
Because the table is for 0.1 molar.
Yeah, exactly. So if you mix 0.2 and 0.2, you get 0.1. Yeah, no, don't do that. No. So you would just look here and you would say, I have, what was it? Calcium with hydroxide would form a precipitate, and strontium with sulfide would not form a precipitate. So you would get C. Yes? Is good? Yes. Number 20. Okay. A precipitate of lead chromate is formed by mixing solutions of, that should have an S. Mixing solutions of potassium chromate and lead nitrate. It would be possible to redissolve this precipitate by adding a concentrated solution of, so we have this precipitate here, and we want to redissolve it. So we need one of these two concentrations to go down, to drag it to the right. Yes? To redissolve more. And we have a second equilibrium here where chromate will react with hydrogen. So if chromate reacts with hydrogen, that's going to cause the chromate to decrease. Okay, so that's going to cause the chromate to decrease. So that's the one that's actually happening there, and that will cause it to shift to the right. Make sense? Very good. Yes? 52. In an experiment, they mix 0.002 molar and 0.004, the trial ion product. Do you guys know what the trial ion product is?
Q.
That's Q, okay? And so we have concentration of Pb2 plus times I minus squared. So we have 0.002 times 0.004 squared. (3.2 times 10 to the negative 8? Oh! Oh! Not 3.2 times 10 to the negative 8, no.
Is the right answer in the answer key.
Oh, well, that's wrong. Okay, so we have mixed equal volumes. So this would have to be half 0.001, and this would have to be 0.002 squared because we mixed equal volumes. The concentrations are halved. Yes, which is what I did wrong, which is no good. So we have 0.002 squared times 0.001 equals 4 times 10 to the negative 9. So it should be A. Okay, number 52 should be A. Fix. Demi. 84. Consider the following, which would cause the solid to dissolve. So again, we need to have something that will decrease the concentration of calcium or decrease the concentration of carbonate, right? Because that will cause it to shift to the right. So it's obviously not going to be the things that contain calcium. It can't be anything that contains carbonate. So even if you don't know why, you could guess that it is HCl, because the other three obviously don't. But do you remember what happens when we put hydrogen with carbonate? Yes? Yeah, we get carbonic acid. And then what happens? It becomes water and CO2. So this is actually an equilibrium. However, this one, the carbon dioxide can then escape, and so that will drag this whole thing that away. Yeah? Because carbon dioxide is a gas. Amy. 13.
Also, 8 right after that.
8 and 13. 13 and 8. Yep. Silver acetate. Crystals are in equilibrium with a saturated solution, which would cause more silver acetate to dissolve. Okay, so we have Ag, CH3, COO, solid in equilibrium with Ag plus CH3, COO minus. And what if we add some AgNO3? Will that cause more to dissolve? No, that's going to cause less to dissolve because we have some silver there. What if we add some NaCH3COO? Will that cause more to dissolve? No, because it'll cause less to dissolve because that's a common ion. Yes? It would cause the equilibrium to shift to the left. If we evaporate some water, will that cause more to dissolve? Do things dissolve in less water? No. So we've eliminated A, C, and D, so it must be B, but let's figure out why. Yes? Concentrated nitric acid, HNO3. What kind of acid is HNO3? It is a strong acid, so it is going to completely dissociate into H plus and NO3 minus. Which of those two ions do you think is having an effect on this equilibrium?
H plus.
H. And if H is having an effect, which ion do you think it is affecting? CH3CO. Oh, because this is a weak base. Yes? So this will combine with the H plus. And this is another reason why I like doing the solubility unit after the acid-base part 1 unit, is because questions like this come up. And it's kind of nice to be able to refer to them intelligently rather than like, oh, you'll learn this later. All right. Are we going on to number 8? Number 8. Given the KSP is that. Okay, so we again have, we've got a dilution here, but it's not a 1 and 2 dilution, so we do have to do a little calculation. So we have 8 times 10 to the negative 8 molar calcium. And we start with 30 milliliters and we finish with 40 milliliters. For fluoride, we start with 3 times 10 to the negative 2, and we start with 10 milliliters and we finish with 40 milliliters. So we have... Well, you don't have to use the Noon method. You can use M1V1 equals M2V2. It'll give you the same thing. You have to use a dilution calculation of some kind. Yes. Does that satisfy you then? Okay, so we're not going to do the rest of that question? Okay. Anyone want the rest of this question? No. Taranyo. 19. Which of the following has the lowest solubility at room temperature? I know for sure it's not zinc nitrate, right? Because nitrates are always soluble. So I'm guessing that I just need to look at my table of solubilities and say which one is low solubility. I'm guessing it's carbonate because carbonate is down at the bottom of the table and the things at the bottom of the table are the most low solubility with everything. But let's go check. Zinc chloride. Zinc is soluble. Zinc sulfate. Zinc is soluble. And so indeed it is zinc carbonate, which is the lowest solubility.
So just like as we go down the chart, like
mostly things like you'll notice up at the top, it's like these things are always soluble. It goes by negative ions, right? And then as you go further down, you've only got 3 things here. You've got 5 things here. You've got most things with some exceptions, right? And then you go most things with fewer exceptions and most things with even fewer exceptions. Yeah, so things generally get less soluble as you go down the table, at least for the negative ions. Yeah. All right. Whoops, that's not what I wanted. I want that one. Who's next? 78. Uh-oh. No. 78. There we go. KSP for cadmium carbonate is 1 times 10 to the negative 12. What is the solubility of cadmium carbonate? For this one, I would use the multiple choice method of finding solubility, which is, this is a 1-to-1 salt. Yeah? So KSP for a 1-to-1 salt is equal to X squared. Okay, and so then my solubility will be square root of that, except for it's now in grams per liter, so then I'm gonna have to do a conversion as well, because this will give me moles per liter. So this is gonna be the square root of 1 times 10 to the negative 12, which is 10 to the negative 6, 1 times 10 to the negative 6. And the mass, molar mass of, that's moles per liter, times grams per mole. And cadmium is 112.4, 112.4 plus 12 plus 16 times 3 equals 172.4 grams per mole. 1.7 times 10 to the negative 4. There we go. Yeah? Amy? 36 and 40, yes. Which of the following can be used to produce a 0.2 molar solution? This is 36, 36. So if you're going to make 0.2, that is greater than 0.1, yes, which means it has to be soluble. So I'm guessing it's this one because chloride's up at the top of the table and most things are soluble with chlorides, but let's check it out again. And sulfite and phosphate are at the very bottom of the table. They're low solubility with almost everything, and hydroxide's fairly low down as well. So let's check it out and make sure. Beryllium chloride indeed is soluble. Beryllium hydroxide is low solubility, and beryllium phosphate and carbonate and sulfite are all low solubility. Okay. Oops. 36 and now 40, 40. In a saturated solution of zinc hydroxide, the zinc is, now we see this 0.1 molar, yes? I'm guessing that we're looking at, is this substance soluble or not soluble? So let's go look up zinc hydroxide. I think it's low solubility, but let's check. Yeah, zinc is low solubility with hydroxide. So that means we cannot make 0.1 molar, so its concentration is going to be less than 0.1 molar because it's low solubility. Yes? 119? 16, 116. What is the solubility of lead chloride in 0.15 molar solution of HCl? All right, so what we've got is we have concentration of chloride is 0.15 molar. We know that KSP is 1.6 times 10 to the negative 5. And we need to know the concentration of lead chloride. So what's going to happen is you're just going to do it like this, and I'll show you why in just a second. KSP is equal to lead times chloride squared. And so we want lead, Pb, 2 plus is equal to the KSP over chloride squared. And so KSP is 1.6 times 10 to the negative 5 over 0.15 squared. 1.6 E5 negative divided by 0.15 squared equals 7.1 times 10 to the negative 4. Now, why did that work? Yeah, because concentration of lead chloride is going to be the same as the concentration of lead, right? And this is our solubility. Why do I not really care about the fact that there is some lead or there is some chloride coming from the lead chloride when it dissolves? Yes. If what I'm doing is I'm assuming the concentration of chloride from PbCl2 is insignificant compared to concentration of chloride from HCl. And if it turns out that, let's see, chloride would be twice that, so that would be what? 7.1 times 10 to the negative 4 times 2 equals 1.42 times 10 to the negative 3. Let's just assume that that's correct. My concentration of chloride from the HCl is 0.15 molar. This would be from PbCl2. Oh, 0.148, which would round to 1.15. Yes, so it is indeed insignificant. Now, do you want to go through the whole thing and prove it? You could. You could be like, okay, I got lead chloride, PbCl2, Pb2 plus 2Cl minus, and I'm starting with 0, and I'm starting with 0.15, and then plus x, and that's going to be x, and that's going to be 0.15 plus x, and then I would have to do the math on this, yes, so I would have to be like, okay, KSP is equal to the concentration of lead times the concentration of chloride squared. And the KSP is 1.6 times 10 to the minus 5. 1.6 times 10 to the minus 5. Lead is x. This is 0.15 plus x. Do you guys want to solve a quadratic? No. And what would we do if this were the acid-base section and we had to solve a quadratic? Well, we did an ice table. This was a rice table. Here we go. ICE. How could we fix this so we don't end up with a quadratic? Which it turns out that it actually is. Yes? If you want to go and solve it and prove to yourself that it is smaller, you go ahead and do that. I am not solving a quadratic because we are not required to do that in Chemistry 12. Yes? Okay. And because this is a multiple choice question, you don't need to write down that you're making that assumption. You just need to be okay with making that assumption. Okay? I saw a hand. Amy. 117, yes. In which of the following solutions is silver chloride the least soluble? So we have AgCl in equilibrium with Ag plus Cl minus. And this gives us chloride. This gives us chloride. Does lithium and nitrate have any effect on this equilibrium at all? No. So this is no effect. This lowers solubility. This lowers solubility. Why does it lower solubility? Common ion effect, it increases the concentration of chloride, so this system will shift to the left, so you will have less dissolved solid. Yes? Now, so I have three things that lower the solubility. Which one will lower it the most? Yes? Oh, which one will lower it the most? CaCl2, why? Because you have two of these, which means the concentration is going to be 0.181 times 2 equals 0.362 molar chloride, whereas the other ones are 0.181 molar chloride. So you have twice the amount of chloride, so it will shift it that much more to the left and make it less soluble. Yes? 119. Which of the following substances, when added to calcium carbonate, will decrease the solubility Okay. So we want to decrease the solubility. So what will sodium and chloride do? Will they change the solubility? No change. What will HCl do? Will it change the solubility? It will. Why? Because H gets together with CO3 2 minus and forms H2CO3, which then becomes H2O plus CO2, which causes carbonate to decrease. Is that going to cause calcium carbonate to be more or less soluble? More soluble. Oh, that didn't help us. How about CaCl2? That will cause it to be less soluble because we've got calcium ion that will increase the concentration of calcium, leading to a shift to the left. And then, we can look at the other ones. This one is going to be more soluble because it's got the hydrogen. This is going to be what about adding CaCO3? What does that do to the solubility? There'll be a bigger pile. Yes? So you'll have sped up the forward rate, but you'll also have sped up the reverse rate because the surface area will be greater, so there won't be any more dissolved. All right, who's next? Brian.
What does like hard water do?
Okay, 41. Hard water refers to water with minerals in it. Usually calcium and magnesium, but let's see. 41. So, do you actually need to know what hard water is to solve this problem? No, you don't. Hard water is just water with minerals in it. So literally, yeah, calcium and magnesium. C? No, B. B. Yes, B. There we go.
Like, it's not in the video, but like the last quiz that we did, like we like the took both of the answers for MgCl2.
Yes.
I was wondering why.
Okay, so you're talking about the one where we had MgOH2?
Yeah.
So this is from the last quiz. Or not from the last quiz, it was from the quiz before. Yeah. And we were asking which of the following would make it the least soluble. And I think the two choices that we had were Mg, Cl2, and NaOH. I accepted either of those, yes. Because both of them contain a common ion, and we had not yet done any math. So I didn't expect you to be like, oh, well, let's do all the math around this and see which one makes it less soluble.
So you have to do the calculation.
Well, in theory, yes, but that, like I said on that quiz, so I would not ask you that question with those options anymore, but I did it because we have not yet done the math. Okay?
Because I was just
Yeah, it would actually be the hydroxide because it's a squared term. Yeah? So it would make it less soluble. Yes? 61. In which of the following would silver chloride be the most soluble? So we're looking for either silver or chloride, which would make it lower solubility. So I've got chloride. That would make it low solubility. I've got chloride and I've got silver. All of those are common ions, which means that the one in which it would be the most soluble would be NH4NO3 because that does not have a common ion. So it's not pushing that equilibrium the other way. Yeah. Any more? In the book? Yes. Pardon me? Uh-huh. Yeah. Come show me and then I can put it on the overhead. Yeah. Is that our electrolytes section?
Technically it does, right? Self-ionization.
But it's so small compared with, like, I mean, 10 to the negative 7, how much electricity are you going to conduct?
Like, when I think of water conducting electricity in our environment, it's not pure water.
It's like got stuff in it. Yeah. Hard water. Yeah.
Okay, that makes sense.
Yeah. Anything else? Brian? Huh? 67. 67, we have that equation, and we have fluoride, which is 1.68 times 10 to the minus 2. So that is the concentration of fluoride. And that means that the concentration of iron, don't worry about it, I'll get it later. What would the concentration of iron be? Half that, 8.4 times 10 to the minus 3. And what would the concentration of FeF2 be? 8.4 times 10 to the minus 3. So what is the solubility of,
Minus 3.
oh, this should be minus 3. I need to fix that. Yeah, that should have been a 3 there, because otherwise that question does not work. Thank you. Yeah. Anything else? Okay, so today you guys picked up a copy of the AP solubility stuff. Yes? And I'm just going to leave that with you. You can do it now. You can do it later. And I will say that people who say, oh, why would I bother doing parts A, B, and C? Those are all to do with things that are not on my test on Wednesday. Well, they will be on your test in May. So we make our choices, right? So if you choose to just be like, I will only do the parts that have to do with actual solubility, that is a short-sighted vision, okay? If you're like, I'm only going to do the parts with solubility up until like after the test, and you do them right after the test, that is a different choice, and that could be a good choice too, okay? But use your time wisely, all right? I know that you've got other classes going on and whatnot, but make sure you do actually do that extra review of like the stuff from last year, okay? And with those ones, I would always recommend sitting down for whatever it says, the 10 minutes or the 20 minutes, and just doing that one question for just that length of time. So you start getting in the idea of this is the pacing that I need to maintain to finish that exam. Yes? Okay, excellent. Do we have any other questions before we move on back to acids and bases, part 2? Oh, would you like time to do that? No. We can do 72. Which of the following saturated solutions has the lowest concentration of carbonate? I'm going to guess that it is, well, it's certainly not the first one. And I know that carbonates are on the bottom of the table, so I'm guessing all 3 of these things are probably low solubility. So what would I have to do if they are all low solubility? I could do the math, or
Yes, please.
I could just look at KSP because they're all 1-to-1 salts, right? And I could say I've got magnesium carbonate, which is times 10 to the negative 6. I've got, calcium carbonate, which is times 10 to the negative 9. And what was the third one? Strontium. Strontium carbonate, which is times 10 to the negative 10. So who is the least soluble? Strontium times 10 to the negative 10. Oh, D, yes, there we go. It has the lowest KSP. Yes? Do you have a quiz on Thursday? No. No. You have a test Wednesday. Unit 3 test? Oh, you mean last Thursday? Yes, we did have a quiz. It was the math one. When would you like to do it?
I think it was on the Wednesday.
I don't know when it was. It was last week, and Justin was away. When would you like to do it, Justin? Yeah? If you do it tomorrow, okay, so you come in tomorrow and maybe during class, you write it? Is that okay? Because then I can mark it at lunch. And you can come during class and get it back. Does that sound good? Yeah, because it's not going to take me too long to mark one quiz. It's only when they're in bulk that it takes a long time. Yes? Yes. Hang on. One of them I may have left at home because I'm a little bit stupid, but you got perfect on it, so you knew what you were doing. No! Did I leave them all at home? Am I an idiot? No? Okay, hang on, hang on. Do I have yours here? There's 3.2. 3.1 you got perfect on. Okay. All right, any other questions? Acid base 2? All right. So we got to page 24. So we were looking at amine functional groups. Do you guys remember what an amine is? No? Which element does it contain? Which one? Nitrogen. And you know what? Amine. Yes? Nitrogen. And they are found in many organic compounds, including amino acids. So the amine is the amino part. The acid part of the amino acid is a different functional group. Do you guys know what that one's called? Carboxyl. Is that right? Carboxyl group, which gives us all of the, what kind of acids? Carboxylic acids. And those are the ones that contain the COOH group, which looks like this. R, what does R stand for? The rest of the molecule or random stuff. Okay, doesn't really stand for either of those things, but we'll say that. Could you guys put lone pairs on that molecule? Could you put lone pairs on that Lewis structure? Not on the R, obviously. Where would you need lone pairs? On the oxygen. How many on that top oxygen? 2 lone pairs, because that gives you 8 electrons in total, yes? How many lone pairs on the oxygen to the right? 2 lone pairs, because again, that gives you 8 electrons. Excellent. All right. Functional groups and organic terminology is not part of the AP curriculum. Okay, so you do not need to be able to spout any of this stuff. But it is nice to recognize that amines have N's in them, because if they bring it up, you know, I need to use a K. What kind of K? with an amine because amines are bases. You need to use a Kb, okay? All right. So here are the reactions of amines with water, and you should be familiar with this first one. Okay, we have NH3 plus water, and one of the hydrogens in water moves over to the NH3, and we end up with NH4 plus. And what's left over from the water? OH. So this is how they all work. So we have N2H4, and what will happen? Water will give it a hydrogen. What?
Why they're bases.
This is why they're weak bases, yes. Yeah. And the reason that they can do this is that they all have a lone pair on the nitrogen. So for example, if we have NH3, and you have a hydrogen coming along, it's got no electrons, right? The H plus. So it can just tack right on there. Yeah? That extra lone pair can be like, hey, hydrogen, would you like to hang out on these electrons with me? And then there's going to be a plus charge on it.
Wait, is there always going to be a lone pair?
Yes, there will always be a lone pair on the nitrogen, because if you remember what nitrogen looks like, just the nitrogen atom, it's got a lone pair. It's got 3 unpaired electrons. So it'll have a bond. It'll have 3 bonds and then 1 lone pair, and that lone pair is what can bond to the oxygen. Or not the oxygen, the H plus ion, sorry. Okay, do you need to really be able to do these? No, you just need to be able to stick an H plus on that. If you're told it's a base, just stick an H plus on it and stick it, where does it go? If you've already got some H's, just put it with the other H's. If you don't have any H's, just put it beside the N. I don't think you need to know this, but just in case. This is just in terms of writing the formula. It always goes on the, it always attaches to the N. Okay, and you can see over here, once again, oh look, here's my N, and the hydrogen attaches to the N, and it just gets written along with the other H's.
Wait, it's a
This means with. It is from the Latin cum. You graduate sigma cum laude?
What?
Have you ever never heard of that? No? Magna cum laude, sigma cum laude, with honors? Pardon me? It was in suits, there you go. It's a way of graduating with honors. Laude means honors. Cum means with. I'm not going to write it because it doesn't look good. You can think of that if you want to. Looks bad. Where do you put the hydrogen ion accepted from the water? You put it on the Nitrogen. Okay, basically it goes on the N. So try writing the equations for the reactions of these following amines with water. So the only one that might be a little confusing is the very first one, because you might think that these hydrogens are on the nitrogen, but they're really not. Okay, because what you would have is you would have C5H5. That would be like CN, C, C, C. I'm guessing this is the structure, right? Yeah, that looks right.
Who's the, like, on the top, what's it called? Is it like just fall like shit?
Oh, that's called resonance. Resonance. Resonance structure. So if you wrote it in the other position, that would be a resonance structure. And but are those electrons really, do they flip back and forth between the two? Like would I go from, they're evenly distributed. So what would be the bond order of the carbon-carbon bonds in this ring? 1.5. Okay. All right, finding the pH, OH, pH, and POH for a weak base. Now, this is very similar to Ka, except for it's Kb. So you have to remember that when she makes it to, after shooing away the crows, she picks up her bag of rice and she makes it to home base. Okay? Home base. And so if you have a base, the little old lady, the rice is no longer on the ground, so what are the crows going to eat? They found some kebab on the ground.
Where did that come from?
I don't know. Your imagination. Okay, they found some kebab on the ground to eat. Aren't they happy? Kebab, kebab. Kb, Kb. I mean, it's all very silly, but like so many times people don't remember that when it's a base, you need to use Kb. And they try to make it a Ka, which confuses me no end, and usually confuses the person as well because they can't make it work because they're like, I'm not getting the right answer, and I can't, it just confuses everybody. Everybody's confused. So if you have a base, use Kb. All right. Oh, look at this. I'm just giving the same explanation here. I know I'm a little too obsessed with this story, but I want you to remember, if she makes it to home base, the crows need to eat kebab and use Kb. All right. So every time you do an acid-based question and it asks you for any of H, OH, pH, POH, you need to ask yourself, is it an acid or a base? Is it strong or is it weak? This, hugely important. Ask yourself that every single time. Just because a question asks you for hydrogen does not mean you have an acid. It could mean you have a base, you have to solve for OH and then change it into H. you need to look at your substance and see if there are clues in the question that tell you. Like, for example, if I was to give you H2CO3, you would be like, aha, that is an weak acid, yes? Right? And you know what another clue is? Look at this. You're given a weak base. What is that? That's going to be a
Maybe.
base, right? You know, like, I mean, the clues are not subtle. Usually, it's just you need to remember to look for them. All right, so here we have, and we want to calculate the H plus ion concentration. And this is the problem, is that people want to have an H plus in the products. But you're told that this is a weak base, and you're given a Kb. So this weak base aniline, C6H5NH2, what does it act as? It acts as a base, accepting hydrogen from water, and water acts as the acid. And I think with that in mind, you could probably do the rest of this question yourself. Why don't you give it a try? And do you remember how the concentration we gave you for a weak acid, was it always initial or final? It was always initial. So what about the weak concentration of a weak base? Will it be initial or equilibrium? It will always be initial, just like weak acids. So our 0.1 molar is the initial concentration. Well, would you like to solve a quadratic equation? Then make that assumption. Yeah. Did you guys get 6.55 times 10 to the minus 6 for x? Yes. What is x? It's the concentration of OH. Is that what I was asked for in the question? No. We were asked for H plus. Do you guys remember how to do that? Yep. Did you guys get 1.5 times 10 to the minus 9? Yeah. Is that pretty much just exactly like doing Ka calculations except with Kb? Yep. Okay, so there's nothing new there really to speak of. All right. Now we're going to do this next one because sometimes you will find morphine. Yeah. Sometimes you will find that the formula is big and ugly and you're like, oh my God, do I have to write that whole thing? So morphine is an addictive painkiller and a weak base. It is the principal molecule in the milky juice that exudes from unripe poppy seed capsules. What is the Kb of morphine if a 0.15 molar solution has a pH of 10.5? Wouldn't it be nice if we could avoid writing C17H19NO3, which is long and awkward and just ugh. And where do I put the H? Ugh. Actually, there's no problem. You can just stick it on either end. Yes? You can just stick an H on there. When in doubt, just stick it on either end. However, you can say, let B represent, or you could even just say B, let B be the formula for morphine. Yes? And then at that point, now if you decide to do this and you don't make the let statement, you will lose a half a mark. So you can choose to be like, I don't want to forget to do that, so I'm going to write out my whole C17H19NO3 plus H2O gives, where do we want to put our H? I'm going to put it on the end. C17H19NO3H plus OH minus. So you could do that, or if you do this, you could say B plus H2O gives BH plus, or you could say HB plus if you want to, plus OH minus. Either of those are fine. Yes? Could you solve the rest of this problem? Uh-oh. I've been given a pH. What do I need to do with my pH? pH goes to POH goes to OH. Or you could do pH goes to H goes to OH. Either of those are fine. I usually tend to do pH to POH because subtraction seems less cumbersome than multiplication, and there's less powers of 10 involved. 10.5.
Because mine is not the project. This is. Oh, but this is that they.
You're gonna change it? And if it's working properly, then don't.
Wait, that's one thing.
Yep. Does it make sense that I've done this here?
Oh, yeah.
Because this is much bigger than this one, yes? If they were in the same power of 10 range, then you would have to actually do the subtraction, right? But there's no real point in doing it at this point because it's so much smaller. No, really? Okay, I feel like I pressed a button wrong. Nope, I didn't. Wow, that's weird. The square of 3.16 times 10 to the negative 4 is weird. But that's okay. Did you guys get 6.67 times 10 to the negative 7? And how many sig figs should we have? We should have one sig fig, right? One sig fig, so that would then become 6. No, sorry, not 6. 7 times 10 to the negative 7 is the Kb. Yeah? Okay, very nice. No, I was just kind of weirded out because when I squared 3.16 times 10 to the negative 4, I got 1 times 10 to the negative 7, like exactly. And I'm like, ooh, that's a weird number, but it was correct.
Well,
How did the acid-base stuff go from this weekend? You did it? Yay! And it was all right? You're like, I don't know. Was it all right or was it not all right? It was fine? Okay, good. All right. Yeah, we have time for one more question. Let's finish this up. Oh, look. We have a certain weak base. Tells us as a base, that tells us we're using Kb. Oh, and it gives us a Kb. So let's use Kb. And it says, what is the concentration of this base? Do we mean the initial concentration or the equilibrium concentration? Initial concentration. And we have pH is 10.16. Good Lord. Okay, we do not know the formula of the base. What can we write? Let B be the formula of the base. No, we do not have the initial.
Oh, it's spent.
Yes.
BH plus.
Yes, it is BH plus. Thank you. What do I do over in that B column? What do I start with? X, because that is my unknown. Yes, I want to know the initial concentration.
But there wouldn't be any sort of like base.
Huh? There's no Kb table. No, although we'll find out how to find Kbs from our Kas. So much fun. Fun awaits us.
Moved it wrong. It's like,
No, I moved it wrong.
yeah, it's like this. Hold on.
Did you guys get 0.0250? Yay! 3 sig figs, I think. Oh, hang on. Yeah, we got a KB. Oh, no, 2 sig figs because of the pH. Why don't I just erase that? There we go. So we have now done all the types of Kb calculations, which are just exactly the same as all the Ka calculations, just with Kb's instead. So that is it for that. There are some exercises. We'll leave those until after your test. Tonight, I would like you to go home. I would like you to finish off your review. If you have finished the review, I would like you to do the AP review that I gave you today. Okay, so if you have not finished the review, go finish the review. If you have finished it, go do the AP review.
It sounds like exactly the that.
You don't need to know the steps of the titration, no. No. For the AP exam, you should be able to describe it because that's one of the things they can ask you to do is they're like, how would you determine the concentration? Here's some equipment. What would you do? Yeah.
You like.
Yeah, that's what I thought.
No, because you did it wrong. And no,
No, this one was like even worse.